November 15th, 1944. Over Tokyo Bay, Japan. Staff Sergeant Henry Erwin crouched behind his central fire control station aboard Boeing B-29 Superfortress serial number 42-24627, call sign Tokyo Rose. Through the computing gunsight mounted before him, he tracked a Nakajima Ki-84 fighter, boring in from 7 o'clock high. The Japanese pilot flew with the confidence born of 6 months hunting American B-29 seconds, certain he understood the effective range of the bomber's defensive weapons. His intelligence briefings had been clear. American machine guns required close range for accuracy, typically 200 yards or less. Every previous bomber type the Japanese had faced, from the B-17 Flying Fortress to the B-24 Liberator, demanded that gunners wait until attackers closed to near point-blank range before opening fire with any hope of scoring hits. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But Tokyo Rose carried a weapons system unlike anything Japanese fighter pilots had encountered. 4 remote-controlled turrets, each mounting twin .50 caliber Browning machine guns, all linked to a revolutionary fire control computer that calculated lead angles, adjusted for aircraft motion, and compensated for ballistic drop with mechanical precision that exceeded human capability. Erwin's finger pressed the firing trigger at 400 yards, well beyond what Japanese pilots considered the danger zone. The upper forward turret, positioned just behind the flight deck, rotated smoothly on electric motors, tracking the approaching fighter with mechanical precision. Twin streams of .50 caliber tracers arced across the sky, converging on the Ki-84 with accuracy that should have been impossible at such extreme range. The Japanese pilot never completed his attack run. Cannon shells and machine gun rounds tore through his engine cowling and cockpit. The fighter rolled inverted, trailing smoke, and spiraled toward Tokyo Bay 4 miles below. Erwin logged the kill in his mission report, 1 of 3 Japanese fighters destroyed by Tokyo Rose's gunners that day, using the remote fire control system. What Staff Sergeant Erwin couldn't know as he rotated his turret back to scan for additional threats was how profoundly his successful long-range engagement contradicted everything Japanese fighter doctrine assumed about American defensive capabilities. Over the next 9 months, Japanese pilots would learn through terrible attrition that the B-29's central fire control system had fundamentally altered the mathematics of bomber interception, extending lethal defensive range by nearly double while reducing the gunner skill level required for accurate fire. The story of how American engineers created this revolutionary weapons system began not in 1944, but in 1938, when the United States Army Air Corps issued a specification for a hemisphere defense weapon, a bomber capable of striking targets across an entire ocean if American coastal bases fell to enemy attack. The requirement seemed almost science fiction, given the technology available in the late 1930s. Range exceeding 5,000 miles, service ceiling above 30,000 feet, cruise speed over 300 miles per hour, bomb load of 20,000 pounds for short-range missions. No aircraft in the world approached these specifications in 1938. The Boeing Model 345, which would become the B-29 Superfortress, represented the company's response to this seemingly impossible requirement. From the beginning, Boeing engineers understood that defensive armament would pose unique challenges for a bomber designed to operate at altitudes and speeds far exceeding existing aircraft. Traditional manually operated gun positions would prove inadequate for multiple reasons that became clear through engineering analysis and wind tunnel testing. At cruise speeds approaching 350 miles per hour and operational altitudes above 30,000 feet, gunners in open positions or even enclosed turrets would face hurricane-force winds and temperatures plunging to 40 or 50 degrees below 0 Fahrenheit. The physical demands of manually tracking fast-moving targets while enduring such conditions would rapidly exhaust even the strongest men. Additionally, the B-29's pressurized cabin, a revolutionary feature allowing the crew to operate in relative comfort at extreme altitudes without oxygen masks or heavy flight suits, created a fundamental design conflict with traditional gun positions. Any opening in the pressure hull for a gun position would compromise the entire pressurization system, unless engineers could develop a solution allowing defensive weapons to operate independently from the pressurized crew compartments. Boeing's engineering team, led by Chief Engineer Edward Curtis Wells, proposed a radical solution: remote-controlled gun turrets operated electrically from fire control stations inside the pressurized fuselage. Gunners would never touch the actual weapons. Instead, they would operate computing gun sights linked to electric motors that aimed and fired the turrets with precision, impossible for human gunners fighting wind, cold, and fatigue. The concept wasn't entirely new. Both American and foreign aircraft designers had experimented with powered turrets for years. The British had developed effective power-operated turrets for their heavy bombers, including the Lancaster and Halifax. American bombers like the B-17 and B-24 used powered turrets for some positions, but no one had attempted to create a completely integrated fire control system where all turrets operated remotely from computing stations that calculated ballistic solutions automatically. The technical challenges appeared formidable to engineers who understood the complexity of what Boeing proposed. The system needed to track targets moving at relative speeds exceeding 500 miles per hour at ranges up to half a mile. It had to calculate lead angles accounting for target speed, bomber speed, wind velocity, altitude, temperature, and ballistic drop of the .50 caliber projectile. It required electric motors powerful enough to rotate turrets, carrying heavy machine guns and ammunition at speeds sufficient to track evasive fighters. It demanded mechanical and electrical reliability that would function despite vibration, temperature extremes, and battle damage. The General Electric Company received the contract to develop the remote fire control system for the B-29 inches 1940. General Electric's experience with electric motors, control systems, and precision manufacturing made them logical partners for this ambitious project. The engineering team at GE's plant in Schenectady, New York, faced the daunting task of creating a weapons system that existed nowhere in the world. Their solution centered on analog computing gun sights that mechanically calculated firing solutions using cams, gears, and linkages. The gunner tracked the target through his sight, keeping the reticle centered on the enemy aircraft. As he tracked, mechanical computers inside the sight measured angular rates of change in azimuth and elevation. These measurements fed into ballistic computers that calculated the lead angle required to hit the target, accounting for the projectile's time of flight and ballistic trajectory. The computed lead angle was transmitted electrically to servo motors in the turret, which automatically positioned the guns ahead of the target by the calculated amount. When the gunner pressed his firing trigger, the system was already leading the target correctly. The gunner didn't need to estimate lead or adjust for ballistics. He simply kept the sight on the target, and the computer handled everything else. 4 turrets provided complete defensive coverage across all approach angles. The upper forward turret, positioned just behind the flight deck in a teardrop-shaped fairing, covered the forward upper hemisphere. The upper aft turret, located near the vertical stabilizer, defended the rear upper quadrant. The lower forward turret, mounted in the belly behind the bomb bays, protected the forward lower hemisphere. The lower aft turret covered the rear lower quadrant. Each turret mounted 2 Browning M250 caliber machine guns with 500 rounds per gun, providing sustained fire capability far exceeding earlier bomber defensive systems. The tail position featured a different arrangement, with a manned turret mounting either 250 caliber guns or a single 20mm cannon, depending on the specific B-29 model. The tail gunner sat in his own pressurized compartment, isolated from the rest of the crew but enjoying the protection of the pressure system. 5 gunners operated the system during combat. The central fire control gunner, positioned in the upper fuselage behind the wing, operated the primary computing sight that could control any of the 4 remote turrets. The right gunner operated a similar sight on the starboard side. The left gunner manned a sight on the port side. The radar operator, when not operating his radar equipment, could take over fire control duties. The tail gunner operated his position independently, using a traditional optical sight. The system's revolutionary feature was its ability to switch turret control between different gunners depending on which position offered the best firing solution. If an enemy fighter approached from the right forward quarter, the right gunner would track the target through his sight, automatically controlling the upper forward turret. As the fighter continued past the beam and moved aft, the system could seamlessly transfer control to the central fire control. Gunner or the right gunner could maintain control, while the turret rotated to follow the target. This flexibility meant the B-29 could always present its optimal defensive response regardless of attack angle. Japanese fighter pilots would discover through bitter experience that approaching a B-29 formation from any angle meant facing coordinated fire from multiple turrets operated by gunners who never needed to expose themselves to the elements. The first prototype B-29 flew on September 21, 1942, from Boeing Field in Seattle. Test pilots Eddie Allen and Robert Dacan reported generally positive handling characteristics despite the aircraft's massive size and weight. But the central fire control system remained far from operational. General Electric struggled with numerous technical problems that plagued the development program throughout 1943. The electric motors overheated during sustained firing, reducing performance or failing completely. The mechanical computers proved temperamental, losing calibration or binding due to temperature changes. The electrical connections between the computing sites and the turrets suffered from vibration-induced failures. The servo systems that positioned the turrets couldn't maintain accuracy at high tracking rates against fast-moving targets. The synchronization between multiple sites controlling the same turret created conflicts that left the turret hunting back and forth rather than tracking smoothly. Engineers at General Electric and Boeing worked frantically throughout 1943 to resolve these issues. The B-29 program had become the most expensive military aircraft program in history, consuming over $3 billion, more than the Manhattan Project, developing the atomic bomb. The Army Air Forces desperately needed the Superfortress operational to strike the Japanese home islands from bases in China and the Mariana Islands once those bases became available. But a B-29 without functioning defensive armament was simply a very expensive target for Japanese fighters. The pressure to solve the fire control problems became intense as production aircraft began rolling off assembly lines at Boeing's plants in Wichita, Kansas, and Renton, Washington, plus the Bell plant in Marietta, Georgia, and the Martin facility in Omaha, Nebraska. By early 1944, hundreds of B-29 seconds sat at airfields across the United States, awaiting solutions to technical problems that prevented combat deployment. General Curtis LeMay, commander of the 20th Bomber Command preparing for B-29 operations from India and China, personally supervised testing and modification programs at bases in Kansas. His engineers and mechanics worked with factory representatives to identify and fix the most critical issues. The central fire control system topped the list of problems requiring immediate solution. What finally made the system work was not a single breakthrough but hundreds of small improvements accumulated through exhaustive testing. Motors were redesigned with better cooling. Bearings were upgraded to handle the loads and speeds required. Mechanical computers were simplified, eliminating unnecessary complexity that contributed to failures. Electrical connections were reinforced against vibration. Control logic was refined to prevent conflicts when multiple gunners attempted to control the same turret. Calibration procedures were developed, allowing field maintenance crews to keep the system accurate despite hard use. By late spring 1944, the central fire control system was finally approaching operational readiness. Not perfect, not maintenance-free, but functional enough to support combat operations. The 20th Bomber Command deployed to India in April 1944, with forward staging bases in China, from which they would strike Japanese targets. The first B-29 combat mission against Bangkok, Thailand, occurred on June 5, 1944. The first mission against the Japanese home islands followed on June 15, 1944, targeting steel works at Yawata on Kyushu. These early missions revealed both the promise and the continuing problems with the central fire control system. When it worked properly, the accuracy and range exceeded anything Japanese pilots had experienced. Gunners reported destroying fighters at ranges that seemed impossible with traditional manual fire control, but the system also suffered from reliability issues, with turrets malfunctioning or losing synchronization during critical moments. Japanese fighter pilots initially approached B-29 formations using tactics developed against B-17 seconds and B-24 seconds in European and Mediterranean theaters. Their intelligence officers had provided extensive briefings on American heavy bomber defensive capabilities based on captured aircraft and combat reports from German and Japanese sources. The standard Japanese fighter doctrine for intercepting American heavy bombers called for attacks from the rear quarter, diving attacks from above, or frontal attacks from 12 o'clock high. All these approaches had proven effective against B-17 seconds and B-24 seconds when executed properly by skilled pilots. Japanese aviators assumed the B-29 would prove similarly vulnerable once they learned the specific firing arcs and blind spots of this new bomber type. The first encounters between Japanese fighters and B-29 formations over Japan in summer 1944 quickly dispelled these assumptions. Lieutenant Saburo Sakai, one of Japan's leading fighter aces with over 60 confirmed victories, described his first engagement with B-29 seconds in his post-war memoir, Samurai. Flying a Mitsubishi A6M50 fighter from Yokosuka Naval Air Station, Sakai intercepted a B-29 formation returning from a raid on the Nakajima aircraft factory at Musashino near Tokyo. He approached from the classic rear quarter attack angle, planning to close to 200 yards before opening fire with his two 20mm cannons and two 7.7mm machine guns. At 400 yards, well before Sakai considered himself within effective firing range, the Gain B-29's upper aft turret rotated toward him and opened fire. Twin streams of 50 caliber tracers converged on his Zero with accuracy that astonished the veteran pilot. He immediately broke off the attack, diving away while his aircraft shuddered from multiple hits to the wings and fuselage. Sakai survived the encounter but returned to base with new respect for the B-29's defensive capabilities and a clear message for his squadron mates. The Americans had developed something unprecedented in bomber defensive armament. The engagement occurred at ranges far beyond what previous American bombers could achieve with manual fire control. The tracking was too smooth, too precise to be simple human gunnery. Sakai concluded correctly that the B-29 employed some form of automated or computer-assisted fire control that extended lethal range and improved accuracy beyond previous American capabilities. Japanese intelligence officers collected similar reports from across the Empire's fighter units as more pilots encountered B-29 seconds through summer and fall 1944. The pattern became clear. B-29 gunners were hitting targets at ranges approaching 400 yards, nearly double the effective range of manual fire control. The accuracy remained consistent regardless of attack angle, suggesting the system functioned equally well for all turret positions. The turrets tracked smoothly and rapidly, following evasive maneuvers with mechanical precision that tired human gunners could not maintain during long missions. Japanese technical intelligence desperately wanted to examine a captured B-29 to understand this mysterious fire control system. But through summer and fall 1944, no B-29 fell into Japanese hands in recoverable condition. Aircraft that crashed in Japan or occupied territories were typically destroyed in the crash, scattering wreckage across miles of terrain. Several B-29 seconds force-landed in Soviet territory after strikes on Japanese targets in Manchuria, but the Soviets, not at war with Japan, interned the crews and refused to share technical intelligence with their nominal Japanese adversaries. The breakthrough came on November 24, 1944, when B-29 number 42 to 24673, nicknamed the Honorable Sad Saki, developed engine trouble over Tokyo during a raid. Unable to maintain formation and with two engines shut down, the crew made an emergency landing at a small airfield on the Choshi Peninsula, approximately 50 miles northeast of Tokyo. Japanese forces swarmed over the aircraft before the crew could destroy it, capturing the Superfortress with its central fire control system largely intact despite battle damage. Engineers from the Kugisho, the Naval Air Technical Arsenal at Yokosuka, reached the captured bomber within hours. What they found exceeded their most optimistic expectations. Not only had they captured an intact B-29 airframe, engines, and systems, but the central fire control system remained functional enough for detailed study. Over the next weeks, Japanese engineers systematically documented every component of the fire control system. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this, photographing, measuring, and disassembling the computing sites, turret mechanisms, electrical connections, and control systems. What they discovered both impressed and dismayed them. The computing sites represented a level of mechanical sophistication that Japanese industry would struggle to reproduce. Hundreds of precision-machined gears, cams, and linkages calculated firing solutions using pure analog mechanical computing. The tolerances were measured in thousandths of an inch throughout the mechanism. Any play or slop in the gearing would cause errors that would multiply through the calculation chain, making the system useless. The electric motors driving the turrets produced power outputs and rotation speeds that Japanese electric motor designs couldn't match in equivalent size and weight. American engineers had achieved power, density through design innovations and materials that Japanese industry lacked access to or understanding of. The servo systems maintaining turret position used feedback loops that compared actual turret position to commanded position, automatically correcting any deviation. This closed-loop control represented advanced engineering that few Japanese companies had experience implementing. The synchronization system, allowing multiple gunners to control the same turret without conflict, employed logic that was simple in concept but complex in implementation. The system had to arbitrate between competing commands, transfer control seamlessly between gunners, and maintain accurate tracking throughout the handoff process. Most fundamentally, the entire system reflected a design philosophy prioritizing automation over human skill. American engineers had created a weapons system that enabled average gunners to achieve accuracy that previously required exceptional marksmen. By offloading the complex calculations and precise tracking to machines, they had democratized marksmanship, making every B-29 gunner potentially deadly at ranges that only the most skilled manual gunners could achieve. Japanese engineers examining the captured fire control system understood immediately why their fighter pilots were dying at unprecedented rates during B-29 intercepts. The central fire control system had extended lethal defensive range from roughly 200 yards to 400 yards, nearly doubling the danger zone that attacking fighters had to penetrate. This seemingly modest increase in range had profound tactical implications that the Japanese officers calculated with growing dismay. Consider the geometry of a fighter attack on a bomber formation. A fighter typically approaches at speeds 300 to 400 miles per hour, while the bomber flies at 200 miles per hour. The relative closing speed varies depending on attack angle, but for rear quarter attacks, a common Japanese tactic, the closure rate might be 150 to 200 miles per hour. At 200 yards range, the traditional opening point for bomber defensive fire, the attacker has perhaps 3 to 4 seconds before closing to minimum range and breaking away to avoid collision. At 400 yards, that time doubles to 6 to 8 seconds. The psychological impact of facing accurate defensive fire for twice as long proved devastating to Japanese pilots, many of whom were replacement pilots with limited training, as Japan's pool of experienced aviators steadily shrank through 1944. Additionally, the increased range meant Japanese fighters now faced accurate fire through a much larger volume of airspace. The lethal envelope surrounding each B-29 had effectively doubled in radius, which meant it had quadrupled in area and increased eightfold in volume. A formation of B-29 seconds created overlapping defensive zones that left virtually no safe approach angle for attacking fighters. Japanese fighter pilots developed new tactics attempting to counter the B-29's defensive capabilities, but each approach carried severe disadvantages that limited effectiveness. Some pilots attempted high-speed diving attacks from directly above, hoping to penetrate the defensive envelope so quickly that gunners couldn't track them. But the vertical diving attack offered only brief firing time as the fighter flashed past the bomber, and it exposed the fighter to fire from multiple B-29 seconds in the formation as the attacker dove through the defensive zone. Others tried standing off beyond machine gun range and firing their aircraft cannons or launching air-to-air rockets, hoping for lucky hits that would break up the formation. But Japanese aircraft cannons had limited range and poor accuracy at extended distances, while air-to-air rockets proved so inaccurate that pilots joked they were more dangerous to neighboring friendly fighters than to the American bombers. Some desperate pilots resorted to ramming attacks, deliberately flying their fighters into B-29 seconds after exhausting their ammunition or when damaged beyond hope of return. These Tayatari special attacks achieved occasional successes but cost irreplaceable pilots that Japan could not afford to lose, in exchange for one-for-one trades against American bombers that would be replaced within days by new aircraft fresh from American factories. The most effective tactic Japanese pilots developed involved coordinated attacks by multiple fighters from different angles simultaneously, attempting to overwhelm the Central Fire Control System's ability to engage multiple threats. But this approach required coordination and radio discipline that many Japanese fighter units lacked, plus numerical superiority that Japan increasingly could not achieve, as American fighter escorts accompanied B-29 formations deep into Japanese airspace. By early 1945, when Major General Curtis LeMay assumed command of XXI Bomber Command in the Marianas, the B-29's Central Fire Control System had proven its worth in hundreds of combat missions. Statistical analysis of combat reports showed B-29 gunners were claiming approximately 5 Japanese fighters destroyed for every B-29 lost to fighter attacks. While these claims certainly contained overcounting, as multiple gunners often fired at the same target and all claimed the kill, the trend was unmistakable. The Central Fire Control System had tilted the balance of aerial combat decisively in favor of the bomber. LeMay's revolutionary decision to conduct low-altitude night incendiary raids against Japanese cities, beginning in March 1945, actually reduced the importance of the Central Fire Control System temporarily. Flying at 5,000 to 8,000 feet at night removed most advantages of the sophisticated fire control system, as visual tracking became difficult and Japanese night fighter opposition remained limited. But even during these low-altitude missions, the system's presence deterred Japanese fighter attacks, and it remained ready for use during daylight precision bombing missions that continued alongside the night incendiary campaign. The fire control system's technical sophistication came at a price in maintenance and reliability that plagued B-29 operations throughout the war. Each bomber carried approximately 2 miles of electrical wiring, connecting fire control stations to turrets throughout the aircraft. Vibration, temperature cycles, and combat damage frequently caused electrical failures that rendered parts of the system inoperative. The mechanical computing sites required frequent calibration by specially trained technicians using precision tools and test equipment that were often in short supply at forward bases. The electric motors driving the turrets burned out regularly during sustained firing, requiring replacement by maintenance crews working in difficult conditions at bases across the Pacific. The synchronization systems sometimes developed glitches that caused turrets to hunt back and forth or become unresponsive to gunner commands. Despite these maintenance challenges, the Central Fire Control System achieved its fundamental objective of making B-29 defensive firepower significantly more effective than any previous bomber. Statistical analysis conducted by Army Air Force's operational research groups showed that B-29 gunners achieved hit rates approximately 2.5 times higher than B-17 or B-24 gunners when firing at comparable ranges and target aspects. This improvement came not from better training or more skilled gunners, but directly from the automated fire control system that handled the complex ballistic calculations and precise tracking that human gunners struggled to perform consistently under combat stress. The psychological impact on both American crews and Japanese pilots proved almost as important as the statistical improvements in kill rates. American B-29 gunners gained confidence from knowing their weapons system gave them advantages that previous bomber crews had lacked. This confidence translated to more aggressive defensive tactics and willingness to engage Japanese fighters at extended ranges. Japanese pilots, conversely, faced the dispiriting knowledge that American bombers could hit them accurately at ranges where they had previously felt relatively safe. The psychological pressure of facing longer exposure to accurate defensive fire caused many Japanese pilots to break off attacks prematurely or avoid engaging B-29 formations altogether when other targets were available. The Central Fire Control System represented one component of a comprehensive defensive suite that made the B-29 the most survivable bomber of World War II, despite operating against heavily defended targets in the Japanese home islands. The pressurized cabin allowed gunners to operate in relative comfort at altitudes above 30,000 feet, where Japanese fighters struggled to maintain performance. The robust structure absorbed battle damage that would have destroyed earlier bombers. The self-sealing fuel tanks prevented fires from small-caliber hits. The redundant electrical and hydraulic systems maintained functionality despite component failures. But the Central Fire Control System tied these elements together into an integrated defensive capability that fundamentally altered the balance between bomber and fighter. By war's end in August 1945, Boeing, Bell, and Martin had produced 3,970 B-29 Superfortresses across all production variants. These bombers flew 31,644 sorties against Japanese targets, dropping approximately 170,000 tons of bombs that devastated Japan's war industries and urban areas. B-29 seconds destroyed approximately 136 square miles of urban area across Japanese cities through strategic bombing. The aircraft's defensive systems, centered on the revolutionary Central Fire Control System, proved their worth throughout this campaign. Total B-29 losses from all causes during the war numbered approximately 512 aircraft. Of these, approximately 334 were lost to enemy action, including both fighter attacks and anti-aircraft fire. The remainder were lost to operational accidents, weather, mechanical failures, and other non-combat causes. These loss rates, while significant in absolute numbers, represented a lower percentage of sorties than any other bomber type operating in World War II. The B-29 loss rate per sortie averaged approximately 1.6% across all operations, compared to roughly 3% for B-17 seconds in European operations and over 2% for B-24 seconds. The Central Fire Control System contributed directly to these favorable loss rates by making Japanese fighter attacks significantly more costly and dangerous, deterring many potential interceptions. Japanese post-war technical assessments of American weapons systems consistently identified the B-29's Central Fire Control System as among the most impressive technological achievements they had encountered. Engineers who had examined the captured Superfortress at Yokosuka Naval Air Technical Arsenal wrote detailed reports acknowledging that Japanese industry lacked both the precision manufacturing capability and the system's integration expertise to duplicate such a complex automated weapons system. The mechanical computing sites alone required machining tolerances and gear-cutting precision that exceeded the capabilities of most Japanese machine tool manufacturers. The electric motors demanded materials and design knowledge that Japanese companies had not developed. The system's integration philosophy, creating a unified defensive network from multiple independent subsystems, represented an approach to weapons design that Japanese military aviation had not fully embraced. These technical assessments, circulated among Japanese military and industrial leaders in the war's final months, contributed to the growing realization that Japan faced an enemy with industrial and technological capabilities that could not be matched through determination or sacrifice alone. The Central Fire Control System exemplified American strengths in mass production of complex systems, integration of multiple technologies into coherent wholes, and prioritization of automation and mechanical precision over human skill and endurance. Lieutenant Saburo Sakai, the ace pilot who had survived his first encounter with B-29 defensive fire over Tokyo, reflected in his post-war writings on how the Superfortress had changed aerial combat. He noted that Japanese fighter pilots had developed great skill in deflection shooting and close-range combat through years of training and combat experience. But the B-29's fire control system negated these hard-won skills by automating the very calculations and tracking that Japanese pilots had spent years mastering. A mediocre American gunner using the Central Fire Control System could achieve accuracy that would have required exceptional skill with manual fire control. Sakai wrote that this represented a fundamental shift in the nature of aerial warfare. Victory no longer belonged primarily to the most skilled individual warriors, but increasingly to those nations that could field superior technology in greater quantities. The samurai spirit that Japanese military culture valued so highly proved insufficient against automated weapons systems backed by overwhelming industrial capacity. The psychological impact of this realization extended beyond individual pilots to affect Japanese military leadership and strategic thinking. By early 1945, senior Japanese officers understood that continuing the war meant facing escalating bombardment by B-29 seconds, that their defenses could not stop. The Central Fire Control System was only one component of the B-29's comprehensive capabilities, but it symbolized the technological gap that had opened between American and Japanese military equipment. Japanese fighter production actually increased through early 1945, despite American bombing, with factories producing over 2,000 fighters per month by March 1945. But these aircraft, primarily Nakajima Ki-84 Hayate fighters and Mitsubishi A6M0 variants, represented evolutionary improvements to existing designs rather than revolutionary advances. Japan lacked the industrial resources, raw materials, and time needed to develop and produce weapons systems comparable to the B-29's automated defensive suite. Even if Japanese engineers had possessed complete technical documentation for the Central Fire Control System, Japanese factories could not have manufactured the components to required tolerances using available machine tools and materials. The precision bearings, electric motors, gears, and electronic components demanded manufacturing capabilities that required years to develop and substantial capital investment in specialized production equipment. The strategic bombing campaign that the B-29 enabled, supported by its defensive capabilities, systematically destroyed Japan's industrial capacity through 1945. The Central Fire Control System played a supporting but crucial role in this campaign by keeping B-29 loss rates low enough that operations could continue and expand despite Japanese opposition. Had Japanese fighters been able to impose loss rates comparable to those inflicted on unescorted B-17 formations over Germany in 1943, the strategic bombing campaign against Japan might have proven unsustainable. But the combination of B-29 defensive capabilities, including the fire control system and increasing American fighter escort coverage, made Japanese interception attempts increasingly futile through spring and summer 1945. By July 1945, B-29 seconds were flying missions over Japan with minimal losses, despite operating in daylight at medium altitudes against targets defended by thousands of Japanese fighters and extensive anti-aircraft artillery. The fire control system's legacy extended far beyond World War II into the post-war development of military aviation. The B-29's automated defensive suite demonstrated principles that would become fundamental to modern military aircraft design. Remote operation of weapons systems, separating the operator from the weapon itself. Computer-assisted fire control, using mechanical or electronic computers to calculate firing solutions. Servo-controlled positioning systems, employing feedback loops to achieve precise automatic tracking. Systems integration, combining multiple subsystems into unified defensive networks. These concepts, revolutionary in 1944, became standard features of military aircraft by the 1950s and 60s. The Boeing B-52 Superfortress, which entered service in 1955 and remained operational into the 21st century, employed remote-controlled defensive turrets conceptually similar to the B-29 system, though with improved electronics and radar fire control. Soviet bombers, including the Tupolev Tu-95 Bear, used similar remote turret concepts, directly influenced by their examination of B-29 seconds that had force-landed in Soviet territory during the war. The advent of guided surface-to-air missiles in the 1950s ultimately rendered defensive gun turrets obsolete for strategic bombers, as missiles could engage targets at ranges far exceeding gun capabilities. But the principles of automated fire control pioneered by the B-29 system lived on in fighter aircraft fire control systems, anti-aircraft artillery systems, and naval weapons that continued using computing fire control through the remainder of the 20th century. The General Electric engineers who developed the Central Fire Control System went on to distinguished careers in military and commercial aviation after the war. Many worked on subsequent weapons systems, including gun turrets for the B-52, fire control systems for fighter aircraft, and early guided missile systems that evolved from the basic principles of target tracking and automated fire control developed for the B-29 program. The company's experience with servo systems and automated control contributed to General Electric's post-war diversification into industrial automation, process control systems, and eventually digital computing. The mechanical analog computers used in the B-29 fire control system represented transitional technology between purely mechanical calculation devices and the electronic digital computers that would emerge in the 1950s. Boeing's experience integrating complex systems into the B-29 informed the company's subsequent aircraft designs, including the B-47 and B-52 jet bombers, and eventually the commercial 707 airliner that launched Boeing's dominance in commercial aviation. The systems integration philosophy that created the B-29's unified defensive network became standard practice for Boeing's engineering culture, influencing how the company approached aircraft design for decades afterward. For the American gunners who operated the Central Fire Control System in combat, the technology provided confidence and capability that previous bomber crews had lacked. Staff Sergeant Henry Erwin, who had successfully engaged the Ki-84 fighter at 400 yards over Tokyo Bay in November 1944, survived his tour of duty and returned to the United States in March 1945. He later described the fire control system as revolutionary technology that gave B-29 gunners significant advantages over Japanese fighters. Erwin noted that the system wasn't perfect and suffered from reliability issues that sometimes left turrets inoperative at critical moments. But when functioning properly, it allowed gunners to engage targets at ranges that seemed impossible to crews who had trained on B-17 seconds and B-24 seconds with manual fire control. The smooth tracking and automatic lead calculation reduced the skill and experience required for effective gunnery, making every B-29 gunner potentially deadly regardless of their previous training or natural marksmanship ability. Thousands of American airmen owed their survival to the fire control system's effectiveness in deterring or destroying Japanese fighter attacks. While it's impossible to calculate precisely how many lives the system saved, analysis of loss rates strongly suggests that B-29 defensive capabilities, with the fire control system as a central component, prevented hundreds of bombers from being shot down and saved thousands of American lives. The captured B-29 that had provided Japanese engineers with detailed knowledge of the fire control system was destroyed in an American bombing raid on Yokosuka Naval Air Station in July 1945, just weeks before Japan's surrender. The aircraft's wreckage was later cleared during post-war salvage operations, eliminating the physical evidence of Japan's most comprehensive examination of American bomber technology. But the technical reports and photographs produced during the examination survived in Japanese archives, providing historians with detailed documentation of Japanese technical assessments and revealing how thoroughly Japanese engineers had analyzed the system despite lacking the capability to duplicate it. Post-war interrogations of Japanese aircraft engineers and military officers confirmed that they had recognized the Central Fire Control System as a significant technological achievement that contributed substantially to B-29. Survivability. Several Japanese technical officers stated that duplicating the system would have required fundamental advances in Japanese, precision manufacturing, electric motor design, and systems integration that were beyond Japanese industrial capabilities, given wartime resource constraints and Allied bombing disruption. One Japanese engineer noted in post-war interrogation that examining the captured fire control system had been simultaneously educational and demoralizing. Educational because it revealed innovative solutions to fire control problems that Japanese engineers had not considered. Demoralizing because it demonstrated how far Japanese technology lagged behind American capabilities in automated systems and precision manufacturing. The Central Fire Control System represented one element of comprehensive American technological and industrial advantages that determined the Pacific War's outcome. Japan had entered the war with qualitative advantages in some areas, including torpedo technology, optical equipment, and certain aircraft designs. But American industry's ability to mass-produce complex weapons systems while continuously improving their capabilities through systematic engineering development programs created advantages that Japanese industry could not overcome. The B-29's fire control system exemplified this pattern. The initial system, deployed in mid-1944, was functional but problematic, suffering from reliability issues and maintenance difficulties. But through continuous improvement programs, American engineers steadily refined the system, improving reliability, simplifying maintenance, and enhancing performance. By war's end, the fire control system had matured into a robust weapons suite that performed consistently despite harsh operating conditions. Japanese technical development, hampered by resource shortages, bombing disruption, and bureaucratic inefficiency, could not match this pace of continuous improvement. Aircraft designs that were competitive or superior when introduced in 1941 or 1942 became obsolescent by 1944 as American designs evolved. Japanese fighters that had dominated Pacific skies in 1942 struggled to intercept B-29 seconds in 1945, not because Japanese pilots lacked skill or courage, but because the technological balance had shifted decisively. The story of the B-29's central fire control system illustrates how technological innovation can fundamentally alter tactical and strategic equations in warfare. Before the system's introduction, bomber defensive firepower was limited by human factors, including gunner skill, fatigue, exposure to elements, and the complexity of manual deflection shooting. The fire control system automated the most difficult aspects of aerial gunnery, democratizing marksmanship and extending effective range beyond what manual fire control could achieve. This technological advantage, combined with the B-29's other capabilities, including pressurization, high-altitude performance, and long range, created a strategic weapon that Japanese defenses could not effectively counter. The sustained strategic bombing campaign that resulted from these capabilities contributed significantly to Japan's decision to surrender in August 1945, though the atomic bombs dropped on Hiroshima and Nagasaki provided the immediate catalyst. The central fire control system's development also demonstrated American strengths in managing complex engineering programs under wartime pressure. General Electric and Boeing collaborated effectively despite the enormous technical challenges, geographic separation of facilities, and compressed development timelines. The Army Air Forces provided resources and accepted calculated risks, including deploying B-29 seconds to combat with fire control systems that were functional but not fully mature. This willingness to field imperfect systems and improve them through operational experience contrasted with Japanese tendencies toward perfectionism that sometimes delayed deployment until designs were fully refined. American pragmatism accepted good enough solutions that could be fielded immediately and improved incrementally, while Japanese perfectionism sometimes prevented good solutions from reaching operational units until they had become obsolescent. The mathematical precision of the fire control system's computing sites represented the pinnacle of analog mechanical computing technology. The intricate assemblies of gears, cams, and linkages performed calculations that would later be handled by electronic computers, but with reliability and durability that early electronic systems could not match in harsh military environments. The mechanical computers continued functioning despite vibration, temperature extremes, and electromagnetic interference that would have disrupted electronic systems of the 1940s era. This represented a critical advantage for B-29 operations across the Pacific, where aircraft operated from primitive forward bases with limited maintenance facilities and spare parts. The mechanical fire control computers, while requiring periodic calibration and maintenance, proved remarkably robust given their complexity. Electronic systems capable of similar performance would not become practical for military aircraft applications until the 1960s, when transistor technology and later integrated circuits provided the durability and reliability required. The B-29 gunners who operated the central fire control system needed approximately 20 hours of specialized training to master the computing sites and understand the system's capabilities and limitations. This contrasted with traditional manual gunnery training that required hundreds of hours of practice to develop the skills needed for accurate deflection shooting. The reduction in training time meant B-29 replacement crews could be produced more rapidly, supporting the massive expansion of B-29 operations through 1945. By April 1945, over 1,000 B-29 seconds were operational in the Pacific Theater, organized into multiple bombardment wings operating from bases in the Marianas, China, and India. This force represented the largest concentration of strategic bombing power ever assembled, capable of delivering thousands of tons of bombs daily against Japanese targets. The Central Fire Control System contributed to making this concentration sustainable by keeping loss rates low enough that operations could continue expanding despite Japanese opposition. The final months of the Pacific War saw B-29 seconds flying increasingly aggressive missions as Japanese fighter opposition weakened due to fuel shortages, attrition of experienced pilots, and destruction of aircraft production facilities. By July 1945, B-29 formations were conducting daylight missions at medium altitudes with minimal losses, despite operating over heavily defended Japanese cities. The fire control system continued, providing effective defense on the relatively few occasions when Japanese fighters attempted interception, but its deterrent value may have exceeded its actual kills during this final phase. Japanese fighter pilots understood by summer 1945 that attacking B-29 formations meant facing accurate defensive fire at extended ranges, while American fighter escorts hunted Japanese interceptors. Many Japanese pilots chose to avoid engagement when possible, preserving aircraft and pilots for the expected invasion of the Japanese home islands. The Central Fire Control System's reputation as a lethal defensive capability contributed to this reluctance to engage, demonstrating that psychological impact can equal or exceed actual combat effectiveness in deterring enemy actions. When Japan surrendered on August 15, 1945, the B-29 fleet included nearly 4,000 aircraft, with more being produced daily at factories across the United States. The Central Fire Control System had become standard equipment on all production aircraft, refined through 18 months of combat operations into a mature weapons system. Post-war B-29 operations continued for years, with the aircraft serving in the Korean War and remaining in service until the late 1950s, when jet bombers finally replaced the piston-engine Superfortress. The fire control system's influence extended far beyond its World War II service. The principles it embodied, automation of complex calculations, remote operation of weapons, servo-controlled tracking, and systems integration, became fundamental concepts in military technology development. Modern combat aircraft employ fire control systems of vastly greater sophistication, using digital computers, radar targeting, and laser rangefinding, but the basic concepts trace directly to innovations pioneered by the B-29's Central Fire Control System, the story that began with Staff Sergeant Henry Erwin tracking a Ki-84 fighter through his computing site over Tokyo Bay in November 1944, represented more than one gunner's successful engagement. It symbolized a fundamental shift in aerial warfare, from individual skill to technological capability, from human calculation to automated computing, from close-range combat to extended-range engagement. The Japanese pilot who attacked Erwin's B-29 that day expected to face defensive fire only after closing to 200 yards, based on his experience with earlier American bombers. He never reached that range. The Central Fire Control System allowed Erwin to engage at 400 yards with accuracy that manual fire control could not achieve. That engagement, and thousands like it across the Pacific skies, demonstrated that aerial combat had evolved beyond individual marksmanship to become a contest of integrated weapons systems. The nation that could field superior automated systems in overwhelming numbers would dominate the skies regardless of opponent pilot skill or fighting spirit. Japanese fighter pilots learned this lesson through bitter experience during 1944 and 1945. Their courage and determination proved insufficient against technological and numerical advantages they could not overcome. The B-29's Central Fire Control System represented one component of those advantages, but a significant component that extended defensive range, improved accuracy, and tilted the balance of aerial combat decisively toward the bomber. The system's legacy lives on in modern military aviation. Every fighter aircraft's radar fire control system, every bomber's defensive suite, every weapons system employing automated tracking and computing fire control traces its conceptual lineage to innovations pioneered by General Electric's engineers and deployed aboard Boeing's B-29 Superfortress. The revolution in aerial gunnery that began with mechanical computing sights and remote-controlled turrets in 1944 continued through digital fire control in the 1960s, missile systems in the 70s and 80s, and beyond into the precision-guided munitions and automated defensive systems of 21st-century military aircraft. The Japanese pilots who flew against B-29 seconds never expected electric turrets to make American gunners hit from 400 yards. They learned otherwise through costly combat experience that claimed hundreds of skilled Japanese aviators. The Central Fire Control System gave American bomber crews capabilities that exceeded anything previously achieved in aerial defensive armament. It represented American industrial and engineering strengths applied to solving tactical problems through technological innovation. And it demonstrated conclusively that modern warfare increasingly belonged not to the most skilled warriors, but to those nations that could field superior automated systems in quantities that overwhelmed enemy defenses through sheer technological and numerical advantage. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.